Today we're going to be talking about sigmatropic rearrangements. But first we're going to recap what we covered in the previous episode relating to electrocyclic ring closures. These ring closures occur when the outermost pi orbitals in a conjugated system rotate to align their orbitals, allowing a new bond to form between them. This rotation can occur one of two ways. Either the outermost orbitals can rotate in different directions, so this one rotating clockwise, this one rotating counterclockwise, bringing the orbitals together in a disrotatory fashion, or those orbitals can rotate in the same direction, so both outermost orbitals rotating in a clockwise fashion, forming the bond in a conrotatory manner. Now, in both cases, the phase of the outermost orbitals when they rotate together need to be matching. So matching phase leads to bond formation, whereas overlapping orbitals with mismatched phases doesn't lead to any stabilization, so bonds do not occur. Now, the factors that are important for this process are whether or not your conjugated system is in the ground state or in an excited state, which we can translate to whether or not you're using light or heat to trigger your reaction. And the other factor is the number of electrons in your conjugated system. So here we have 4, whereas in this chemical species we've got 1, 2, 3, 4, 5, 6. And you need the correct combination of those factors to facilitate electroring closure reactions. But the upshot of all this is that the products that we form by the different methods have unique stereo properties associated with them. So provided you know the number of electrons in your conjugated system, you can choose to either apply light or apply heat to get the product with the stereochemistry of your choice. Here we can see a recap of the orbital arrangement that you would get either for the excited state if you're applying light, or the ground state if you're applying heat. And the biggest difference between the two routes is if we look at the outer two most orbitals of the conjugated system, here we can see the phase of the orbitals are aligned to form a bond by disrotatory closure, whereas on the other side we can see that the orbitals are set up to bond if you rotate them in a conrotatory fashion. Now, the reason why we went through that recap is that this same idea holds relevance for sigmatropic rearrangement reactions. I've shown two common types here. In the top one, we've got a methyl group. We can see it migrates from the 1 position across to the 3 position via this transition state shown in the middle, and we can effectively do the same thing with a proton as well. So a hydrogen shifting from the 1 position across to the 3 position via this transition state. I've shown the transition states as being positively and negatively charged. You could arguably show it as two radical species instead if you wanted to show neutral species. This migration process, it can occur in a similar manner as to the disrotatory and conrotatory mechanisms that we talked about for electrocyclic ring closures. These migrations can occur either along the same face of the molecule, so that's suprafacially, or by switching to the opposite side of the conjugated pi system, which is antarafacially. And we'll cover that in a little more detail now. So the main similarity to what we were talking about before is we're still going to have to be rotating these outermost pi orbitals in order to transfer our group from one orbital to another. There are two ways that we can initially rotate our outermost pi orbitals. If we're focusing in here on the hydrogen as the group that's going to be transferred, we can rotate the transferring orbital in a counterclockwise way and rotate the receiving orbital in a clockwise way, giving a disrotatory process, bringing these two orbitals relatively close together, allowing our hydrogen to be passed across from one side over to the other. Once it's across to the receiver orbital, it can rotate back to where it started, giving us our suprafacial migration, essentially meaning our hydrogen started here below the pi system, it was transferred underneath, and at the conclusion, it's still located here underneath the pi system. So that's one option. For the other option, left-hand side of the molecule is going to be exactly the same. Main difference is, if we look at the phase of this orbital, the receiving orbital, it's been swapped around compared to the suprafacial process over here. So this time the hydrogen can't be passed along the bottom of the molecule, because if it does, it's going to encounter an orbital that has the wrong phase. The solution would be that the receiving orbital is going to rotate in the opposite direction to what we saw before. This is going to bring the orbital with the correct phase down to meet the transferring orbital in the middle, like so. Like before, if the receiving orbital is rotating counterclockwise to access our hydrogen, once it receives the transferred group, it can rotate back to where it started. And if we look at the location of our hydrogen, in the beginning it started at the bottom, it then migrated up across the pi system, and it winds up above it at the end. So that's our Antara facial transfer process. As before, very similar to our electrocyclic ring closures, the orientation of these orbitals, so which direction the phases are facing, is really important to see which of these processes is allowed or forbidden, meaning that whether you do the reaction thermally or photochemically is going to influence which one of these processes occurs. So showing those two migration processes in a more diagrammatic way, if we imagine our group that's going to be transferred, provided our orbitals have a suitable phase to receive our group, they can rotate inwards in a disrotatory manner and transfer the group across in a suprafacial manner. And as you can see, group starts at the bottom, transferred remains at the bottom, like so. If the phases of our orbitals are mismatched like this, they both need to rotate in a conrotatory fashion, transfer the group between them, and the transferred group winds up on the opposite side of the pi system. That's the Antara facial migration pathway. We can consider this using frontier molecular orbital theory. As I was saying before, if you see constructive overlap at both termini, the reaction is going to be allowed. If there's destructive overlap at either termini, the reaction is going to be forbidden. Now, some interesting things can happen if the migrating group is carbon. What you can actually see is an inversion of the stereochemistry or configuration as the reaction occurs. This can't occur for hydrogen because it's typically not going to have any functional groups attached to it. So let's consider an example. We're dealing with thermal conditions and our transferred group is going to be a hydrogen. Because it's thermal conditions, we're going to be dealing with the ground state, which is this one shown here. So this gives us our orientation of the orbitals, providing the phases that we're going to be dealing with. So if we consider our hydrogen bound to a matching phase of a pi orbital, and then we try to transfer it across via a suprafacial migration, we see that there's going to be a mismatched or destructive interaction with the receiving orbital. So because this destructive overlap is seen, this pathway is forbidden under thermal conditions. If we instead consider antarafacial migration, we can see that via this diagonal pathway, whereby the hydrogen is going to wind up on the opposite side of the pi system, this technically looks allowed. We see constructive overlap between all of the orbitals whereby the hydrogen is going to transfer to. Now, while technically this could be allowed, if we think about the sterics involved of transferring a hydrogen atom located up here, diagonally down between these orbitals, and then winding up down here below the pi system, in practice this is too hard to achieve. The sterics simply don't allow it to occur. So effectively, if you tried this reaction under thermal conditions, it's just not going to work. It could theoretically work this way, but sterically, it's just too hard. The orbital orientations just don't work out. Now, if we instead consider photochemical conditions, so we go from our ground state up to our excited state here, which gives us a new configuration of orbitals, we can try again. So if we have a look at our hydrogen, it's going to have a matching phase to the transferring orbital that it's attached to, and we can see that it's also matching the phase of the receiving orbital. So this transfer via a suprafacial migration is going to be allowed under photochemical conditions. If we look at the antarafacial migration pathway, we're going to see destructive interactions, so this one is forbidden, formally and in practice. Now things become more interesting when we now consider carbon as our migrating group. So we're back to thermal conditions and this arrangement of orbitals. If we go back to suprafacial migration and we're using the carbon's empty p orbital, we can see we've got overlap with the transferring p orbital, but destructive overlap with the receiving orbital. So this is going to be a forbidden pathway that you're not going to see under thermal conditions. Here though, the p orbital of the carbon is much more flexible than the s orbital of the hydrogen. So because it has these two lobes, that have different phases. We can line up the carbon groups side on, allowing good overlap with the transferring p orbital, as well as good overlap with the receiving p orbital. So what effectively happens is that the carbon kind of rolls over from the transferring orbital to the receiving orbital. And because we see this kind of, flipping over or inversion of the carbon, any R groups that might be coordinating to that carbon are potentially going to flip around their stereochemistry. So that's where the inversion comes from in the groups attached to the carbon. It's the fact that it rolls over when it migrates across the conjugated system. So now if we consider our photochemical conditions, we've got two matching orbitals here, so the suprafacial migration is going to be allowed. Now considering the different phases of the carbon lobes, this antarofacial flipping mechanism becomes forbidden. We can also consider what's going on by the Dewar-Zimmerman model. Here we have our starting material and we're going to be considering our transition state here. So the question is, entering into the transition state, how many mismatched phase bonds occur? So the initial p orbital interactions are shown here in pink, as well as the interaction between the hydrogen and the transferring orbital down here. So it's shown down here at the bottom because it's not actually part of this sort of conjugated interaction up here. So looking at our transition state, if we're forming this new bond in green when we do the transfer across of the hydrogen, we can see that there are no mismatched phase bonds occurring at all. So we count 0 as being even, so this is going to be a Huckel topology. We need to know the number of electrons in the system in order to assign it as being aromatic or anti-aromatic. So here we can see 1, 2, 3, and the hydrogen is donating an electron into this pi system. So overall, we count this as 4 because of that extra electron donation. So being Huckel and being 4 electrons, this is an anti-aromatic system. And because it's anti-aromatic, we would say that this thermal reaction is forbidden. And looking back to earlier, we concluded exactly the same thing via frontier molecular orbital theory. Now looking at a 1,5 sigmatropic rearrangement, here's our starting point, here's our transition state. We can draw out our initial p orbital interactions, as well as our hydrogen interacting with the other side of the p orbital. We can draw in our final bond, shown here. Again, there are no mismatched phase bonds occurring. That counts as even. Therefore, it's a Huckel topology once more. This time, though, we've got 1, 2, 3, 4, 5, as well as the 1 electron donated by the hydrogen. So this is a 6 electron system, or 4 electrons plus 2. Therefore, it's an aromatic transition state. And because it's aromatic, the thermal reaction is going to be allowed. Last example we're going to consider is going to be a 3,3 sigmatropic rearrangement. Here's our starting material. Here's our transition state where the bond breaks and we've got two radicals, and then finally the bond reforms on the opposite side of the molecule. If we consider FMO theory and we're doing it under thermal conditions, so this is going to be our arrangement of orbitals here in our transition state. As you can see, we can align our orbitals in a constructive manner, shown here in the chair arrangement, so this transition should be allowed. Interestingly enough, we can flip around this top portion and still retain constructive overlap of the orbitals, meaning that this process would also occur in the boat arrangement as well. Just to show that the Dewar-Zimmerman model also agrees with this, we can draw out our 2 3-carbon fragments in the transition state. We can link together the conjugated orbitals, shown here. The black bond, which isn't part of the conjugated system, we draw that as a mismatched phase bond, linking the two systems together. And then finally, the new bond is down here, a second mismatched bond. So, because the transition state has 2 mismatched bonds within it, it's a Huckel topology. It contains 6 electrons in the system, therefore it's aromatic. Because it's aromatic, the thermal reaction is going to be allowed. So that's a whirlwind overview of sigmatropic rearrangements. It has complementary chemical principles to the electrocyclic ring closure topic in the previous episode. Both frontier molecular orbital theory and Dewar-Zimmerman models give useful analyses for these types of rearrangements. Each method relies on different precursor knowledge, but provided you know one of the methods well, you can use them to determine whether or not a thermal or photochemical reaction is going to be allowed or forbidden. That's it for today. Thanks for watching.